Hi there, and welcome to a screencast for algorithms and data structures for mathematicians. In this screencast, we're going to take a look at the binary search method that we saw in class, and we're going to see how we can change it to have the upper and lower bound included instead. Remember that in this current implementation, we make a copy of the list for every recursive call. This happens in line 13 and 15. I've also written two simple tests that check whether the number 3 and the number 7 are in this list, and every time I hit run, it will execute these tests. The output is visible in the area below. Now, to get rid of making this copy, we were going to include a lower and upper bound as extra parameters. So let's start by introducing these parameters. Let's call them lower and upper. Now, our initial if statement checked whether the list was empty. We now have to think in terms of this lower and upper. When do we say our list is empty? Well, the answer is when lower exceeds upper. If our lower bound exceeds our upper bound, surely there are no elements left. Then, to find the middle, we don't take the middle of the list, but instead we want the value that is in the middle between lower and upper. So we add them together, divide them by 2. The rest of the algorithm remains roughly the same, except of course when we call our binary search method recursively. In this case, we need to see how do we need to update this lower and upper value. Well, when our value in the middle of the list is larger than the value we're looking for, we have to move to the left side of the list, meaning our lower bound remains the same, but we change our upper bound to be just below this middle value that we just checked. Similarly, if it turns out that we need to look in the right side of the list, our lower bound becomes the middle plus 1, and our upper bound remains the same. Let's see if this works. It doesn't. Python has thrown an error. Why? Well, because in my little test down below, I haven't included the extra parameters yet. So let's do that. To start looking, we want to start looking between 0, the start of the list, and the length of the list. We want to consider the full list. And there we go. Now it seems to work. Let's try by adding a bunch more tests. Let's see if it can find all the elements in the list. So all elements in the list should be in there. Let's add a few more, and that all seems to work out just fine. And there's one more thing I'd like to change. We've answered now the question of, is the item in the list? Or, if you think of our library metaphor, is the book in the library? And that's great, knowing that it's in the library, but of course I'd like to know where I can find it. So, now that we have this upper and lower bound, it actually becomes a lot easier to find the exact index of the item. Rather than returning false or true, all I need to do is say either I return -1 when I can't find the item, or I return m, the index of the item when I found it. So all I need to do is update line 6 and update line 10. To indicate that I cannot find the item, I will use the value -1. And if I found the item, I'll return m. Let's run our test once more, and voila. 7 isn't in the list, so it returns -1, and all of the other items return their index. Binary search in log n time, that returns the index, rather than just a true or false. That's it for this screencast. Perhaps I'll see you around for another.